Hey everyone, command line interface AI tools are popping up everywhere, yet there isn't one that is local first, one that you fully control, understand, and uses the hardware that you already paid for. They all also focus on coding, but I want something that can do other tasks for me too. So let's build one together. I first want to talk about the architecture a little bit before we dive in. And the idea here is to split it up into two main parts. The AI core, which is going to handle all of the LLM calls, the agentic logic, and the MCP servers. And on the other side, the user experience side of it, this is actual CLI interaction part of it, is going to be its own separate component as well. And within that, starting on the CLI side, we're going to just follow a really simple interaction model. We're going to give the user the opportunity to type a prompt. Once they do that, we're going to call the agent, which we'll talk about in a second. Then that agent is going to be emitting events, so things like messages that it's sending or tools that it's calling, so that the user has some sense of the progress that it's making. We're going to handle that event in the UX, display it, and once we do that, we're going to continue. Once basically we process that event, and then the agent is going to keep going until it reaches some termination condition. Once it does that, the turn's going to end, and then we can again let the user type another prompt. So that's how the UX is going to go. Now for the agent loop, it's going to kick itself off by taking in that user message. Then we're going to look at the MCP servers that the user has configured. So we're going to build in some native ones, things like Filesystem and the ability to fetch content from the web. And also, we want to have that ability to be modular and have the ability to pull in any MCP servers that are out there in the community. So the agent's going to get those tools, get the information from them, and that's going to be wrapped as an MCP. We're going to kind of put that together as an MCP client. From there, once we have the tools, then we're going to have some of our own prompts and format chat completion messages, and then make a call to the model, and then handle the tool calls that are made. And I don't have it shown here, but once we handle tool calls, we go back, format the completion messages again. If any tools are called, we handle them again, and then we keep going until there's no more tool calls. Once we do that, then we stop basically emitting events. The CLI interface of TinkerTasker is built on an event-driven architecture using an event bus. Let's start with what we print to console anytime after a message is sent by the user. That logic is encapsulated in this handle event function, which displays events from the agent and prints them out. There's two types of events that we want to display. One is the assistant response, or the message that the model generates to talk to the user. The other events are the tool messages, which should both be the tool call, or the model saying, hey, let's view this file, and the result of that tool call, which is our MCP server returning the content of that file. Because the LLM generates the tool call, but code generates the actual message, we have a cache to be able to easily associate the tool call with the result of it. Okay. While the turn is ongoing, we also want to show an indicator of progress to the user. So we use Rich's status context manager to be able to do that, and we update it async. And here is where we start a turn that starts the time tracking, and also kicks off the agent, which I'll show in detail later. For now, all that is important to know is that the agent is a generator that yields messages, and then we convert those messages to events that get handled by that handle event function that I just showed. And then to put this together, we send our initial message, set up the agent, and then we use Rich to prompt the user for input. And whenever we do get input from the user, we kick off that process user message function. And that is all there really is to the TinkerTasker CLI. It's meant to be super simple. TinkerTasker uses MCP servers to make modular the core agent functionality and to maintain the flexibility to use any of the community-written servers out there. I implement servers using FastMCP, which is a Python package that lets us easily define MCP tools and other parts of the spec. I have two native servers built in, and here I'm showing the web server first and in more detail because it's the simpler of the two, and the learnings from this one will transfer over to any other MCP server that you want to build with FastMCP. Here at the top, the server is instantiated. You typically provide a name for your server, which helps identify it in client applications, and the client can also use these instructions for extra content on how to use the tool. Then when you see this decorator, that's how you mark this function as a tool that the LLM can call. The goal of this fetch tool is for the model to be able to fetch the contents of a website for any URL that it generates. Usually those will be common websites like news or links that we'll find in your files, or URLs that you give it directly in chat. The arguments to this tool, which in this case is just the URL, are what the model will generate. And it should return a string or something that can be converted nicely into one. Since all of this is meant for the model to use, especially since we're using local models, it's really important to keep this definition simple and clean. And also this docstring here is important because it's actually what gives most of the instructions on how and when to call the tool. So for example, we've written this tool description in a way that puts it in context for the model rather than developers. For example, I say, hey, use this tool when you need to. Then the body of this tool delegates most of the work to one of my other packages, not again AI, to fetch the content. Within this process URL function, it'll use crawl for AI to go to the website and return its content as markdown alongside any links. It also has some other nice features like automatically parsing PDFs and Google Sheets if that's what the URL is referring to. From there, probably the most important step in all of this when you're writing MCP tools is processing the result into something that is friendly for the model. And what this means is that the text should not be too long, or you'll quickly fill or exceed the context window of the model. And you want to use the best practices for formatting the content for the model so that it's less susceptible to getting confused. What I like to do is wrap the content in XML-like syntax. Also, another thing that I do is explicitly parse out the URLs found in the context. I find that doing this is super cool because it lets the model better realize that it can chain together these calls to fetch to do a sort of a web crawl. Like for example, it finds one URL, which then presents to it like 50 URLs, and it can then keep picking them to find what it needs. Next, I'll very briefly cover the Filesystem MCP's key features. It very closely implements these text editor tools from Anthropic, which are view, stir, replace, create, and insert. So flipping over to the code, we have each of these implemented here. If we go down, view, insert, stir, replace, and create. And one thing that I want to highlight is that we're more thorough and about error handling and do it in a way that's clear for the model to understand. For example, if it tries to create a file that already exists at a path, we can give it clear instructions of what it should be doing instead. This is really key to quality MCP servers. And one last general thing that I want to mention before moving on to talking about the agent and talking about LiteLLM is that the nice part about wrapping this functionality as MCP servers is that they can be used with Claude Desktop and any other client that allows for MCP server support, not just TinkerTasker. Alrighty, here's my favorite part, the agent. At its core, it's actually really simple. It just calls tools in a loop. That period of time that it's calling tools in a loop, I usually refer to as a turn. Within a turn, it first fetches available tools dynamically from the MCP client. This is a helper provided by FastMCP. It formats them to the OpenAI tool format because by default they're the MCP standard, but LiteLLM requires the OpenAI standard. We format the prompt, which I'll show in detail in a second, and then we send that request to LiteLLM. When we get the result back from the LLM, we then yield that assistant message back to the caller so they can show it to the user if they want. And then we start calling tools through MCP that the model called, if any. Let's take a deeper look at the system prompt, which we set as the first message to the model when we initialize the agent. The system prompt is where we explain to the model what it's doing, give it context, and any extra information. In the prompt here for TinkerTasker, I first tell it what it is. I explain that its goals are to help users complete their work. I reinforce that it's an agent by telling it to keep calling tools until the task is completed. And I explain that it must first plan before each tool call in order to determine which one to call next. Having the model reason and explain what it's doing before calling tools is usually really helpful to keep it on track for longer. Next, I start by giving it some information about the environment it's in, the knowledge cutoff of the model, and the current date. I tell it that it's inside of a specific working directory. This is something that is somewhat coupled with our Filesystem MCP Server, where we assume that paths will be relative to the directory that TinkerTasker has launched, and it can only make modifications to file in that directory or subdirectories, although note it can read in any files by default. So then we explain to it about MCP, and at the end we will provide descriptions of the enabled MCP servers. And again, the system prompt is the first message that we provide when the agent is first initialized every single time. Now going back to the agent, let's walk through the entire process of prompts. So again, like I just said, this is where in the initialization, the system prompt is appended to the message history. Then when a new turn starts, this is where the user message gets appended. We only append that once outside of the loop. Loop begins, LLM is called, and when the LLM call comes back, we will always append that message that came back, whether it had tool calls or not. And then for each tool calls, we'll append the result of that tool call as a tool message here. Basically, the models have been trained to handle this type of paradigm, where you keep appending the messages, and it figures out the next message to generate next. Briefly, let me also show the LiteLLM function. LiteLLM is a wrapper around a bunch of APIs of our huge variety of different LLM providers, including Ollama, which we use to run our local models. This A-completion function is that common interface that LiteLLM provides, and it takes in a model where the first part of the name determines which LLM provider to route it to. It also expects inputs that align with OpenAI's API, and it handles decently well the conversion to different providers like Ollama. That means that even though I've written TinkerTasker for Ollama in mind, and specifically the Qwen 330B model, it's not too difficult to configure it to use an OpenAI like Claude, OpenAI, or really any other major one out there. I will note here that with Ollama, there were a few tricks to get things working right. One is that the reasoning models will output their internal reasoning as part of the regular response. So I have this function here to filter that out. Basically, you need to filter out everything that's between these think tags. Otherwise, if you don't, the model will start to get confused in future turns quicker. Also, Ollama's default context window is set to be really small, so you need to make sure you set this num_ctx parameter to increase it based on the model you're using and how much GPU memory you have. I think for Qwen 3 that I use in TinkerTasker by default, it has a max of 40,000 tokens. The MCP client is where everything comes together. It manages both native servers like Filesystem and Web that I have, and external MCP servers that users can configure any server out there of their own. This uses FastMCP's composition pattern to mount multiple servers into a unified one. Our goal with this initialize MCP function is to 1, return all of the instructions from the individual MCP servers, and 2, to return the client object itself that we can then use to both see which tools are enabled and which tools actually call them, or to be able to actually call those tools like we saw in the agent. So first, we get the instructions from our native servers and we also check if they're actually enabled because we do let the user disable them in the config if they want. Here's where things get a little bit more interesting with external MCP servers. These are configured with a command to launch them, and this is usually where you usually find this command at the place that you found the server. Like there's different types, some use NPX, some use UV or IP remote servers. And for these, the client has to perform initialization in 2 steps. The reason for that is first we connect to them to get the instructions, because then once we mount them together here, I couldn't find a way to get the instructions from the original MCP server. And then with this, we return the client and the instructions. One last thing I want to do is step through in the debugger to see how all of these different pieces come together. So let me start that debugging session up in main.py in the CLI UX. And we should see TinkerTasker pop up here in just a sec. And I'm going to type a question that will prompt it to call one tool, which is, can you list all of the files in the current dir? We skipped all the initialization. We're going to go into process user message. We're going to see the status start updating. The timer's not going to go because we're paused in the debugger. So yeah, the turn context starts. We'll see that the user message event gets emitted. This just prints a new line. And now we can step into the agent turn. The first thing that's going to happen is this list tools is going to be called. So here we can see the 5 tools that we have enabled, which are all coming from those native servers. 4 of them coming from the Filesystem one, and the one coming from the web MCP server, which is fetch. And these you can see are in the FastMCP format right now. We need to convert these to the OpenAI format to be able to use with LiteLLM. So that's what happens there, and now we can see that they have a different data structure. And we append that user message to the message history, and we get into our agent loop where it's going to call the LLM with Ollama. And here we can also see the parameters that are getting sent to the model. And we're going to step through this. And it's going to take a sec here because the first time the model runs usually takes a little longer since it has to load it in a GPU memory. But in the meantime, I can show some of the parameters. We set this numCTX as 32,000, which is almost at the limit of the model, and we have max completion tokens at 4,000. Okay, it's come back. And if I just step over this, we should be able to see the assistant response, which is in these think tags like I was talking about earlier. And this is that internal reasoning that the model is doing. Usually if you use a reasoning model for this, all of its kind of reasoning about which tools to call happen within this. It won't actually generate any parts of a message after that. So you won't see anything actually in chat. It'll just go ahead and call the tool after we strip out the thinking tags. Okay, so we're going to append that to the message history, and then now we have something that we can yield back to the client, which is that message. Since there was no content there, because after the thinking tags were stripped out, there was nothing left, you actually don't see anything printed to console yet. So then it's going to handle that tool call. So actually, if we go back in this assistant message, we see that there was one tool call made. It was, where is it? Function. We see it was the view tool with a path of dot, which makes sense because we didn't specify any directories. So now what's going to happen is it's going to go into the Filesystem MCP server. And because it's separate, I don't think I can step into this normally. So I'm just going to put a breakpoint on I want to put a breakpoint on the file tool right here. And then I press F5 to get into there. Okay, so we see now that we're in the view tool running this code. You see it's going to try to resolve the path for us based on that relative path. So it resolves it as to the directory that I have the repo installed in, and where I launched the main script from. Okay, and since it's a directory, it's going to go down this directory path. I'm actually going to skip through this until so we can see what it gets formatted as. And we see this result listed 8 paths, which, you know, if we just look at the CLI UX folder, this is 8 paths, if I'm counting correctly. Okay, so stepping back through this, let me go put a breakpoint after the tool. And yeah, we should see now this get printed to the console. Perfect. And then there's no more tools, and now, yeah, we go through the next iteration of the agent loop with that tool result in there. So now what should happen is the model is going to generate the response back to the user, since it now is basically going to synthesize the output of that tool call. So we should see that happening here. Okay, it's thinking. And then eventually the thinking tags will end. Let's see if I can find it. I think it might be too long. So let's just wait and see what it prints to console. Yep, there we go. You can see the assistant message got printed here. There's shouldn't be any tool calls here, so that's gonna skip. Yep. And we're gonna bounce out of all this. And eventually, there's no more user message to process. So we're gonna get back to that input. And there it is. So that's TinkerTasker. If you would like to learn more, please feel free to comment. Thank you so much for sticking around and watching. I hope you'll check out TinkerTasker on GitHub.